Hello students, today we'll be talking about experiments. So I've alluded to experiments quite a few times in the class as one type of research method that we use. So let's talk about experiments in a lot of detail today and how to do a good experiment, how to make sure you're getting valid data, and how you can use an experiment to look at causal relationships. So we recently looked at correlations and how correlations give you a number or a model, so with multiple regression of the relationship between variables, but with experiments we can actually get that A causes B, or is it B causes A, or is it A plus B causes C. All those kinds of things can be discovered through experiments. So let's talk about the kind of controls you need to be able to do an experiment and a bunch of examples of experiments. Alright, so a lot of people have a sense of how things work around us. And we talked about this at the very beginning of the course with kind of the general ideas people have about psychology and science. People feel like they have an intuitive belief about how science works, specifically psychology, specifically all kinds of sciences. So people have this intuitive sense about what's happening with physics specifically. So people's belief about the motion of the objects, intuitive understanding of physics, how gravity works. But the thing is, just like with psychology, it's often inaccurate for physics as well. So an interesting example of this is this short video. So think in your mind, how does the solar system work? How does it move around itself? How does it move around the galaxy? How does the galaxy move around the universe? Oftentimes our intuitive understanding of these kinds of scientific concepts is not correct, and we'll talk about how that's related to our intuitive psychology also not being correct. But it's a really cool video. This is a model, a visual model of how the solar system is actually moving. So, you might have learned something there about how our solar system moves through our galaxy. I had thought I had showed how the galaxy moves through the universe, but it doesn't. But with that, hopefully that gives you a sense of the way we teach things, the way we model things, sometimes gives us an inaccurate perception. So we often think of the solar system on a flat plane, sun in the middle, all these planets around, spinning around the sun, and yes, that's the case. But the sun is also moving through the galaxy. So our whole solar system is trailing behind the movement of the sun as it's orbiting. So all these variables are important to do things like maybe fly to Mars, for example. It's kind of important to know some of this movement. Granted, with relativity, the solar system as a system, you can look at it as an individual and as a system within the bigger system of a galaxy to give you these different kind of models. But it's pretty cool to think of our solar system moving through. You probably didn't consider that kind of trailing following of the planets behind the movement of the sun. So One thing is, yes, that's definitely based on the models you've seen of the solar system's movement and things like that. But also, we have an intuitive sense of how things work, how science works, how objects move, how they interact with each other. And we have a similar kind of thing in psychology as well. People have like common sense psychology topics that we've talked about that are often inaccurate. So people's beliefs about the functions of the mind, its relation to behavior, the textbook calls it folk theories, are very often incorrect. So sometimes they are correct. Sometimes we test it, and that's the big point. You've got to test it. You've got to test theories. You've got to try to falsify theories and see which ones are accurate, which ones are not, which pieces might be useful, those kinds of things. Despite having experience and understanding of humans, human life, a little bit about human mind, we are often incorrect about things. So, how can we figure out how our mind works, how it relates to causes of behavior, all sorts of things? Well, through doing actual scientific methods. So, let's talk about experiments today specifically. And before that, I actually want to tell you a story about Clever Hans the horse. This is a horse that could do math. So you may have heard this, especially if you had a class from me beforehand. I usually share this even in my general class. But this is Clever Hans, a horse. This is Clever Hans' owner, and also in this case you might say experimenter. Here's a board of math problems or numbers. And what this person would do is bring Clever Hans to the city and say, hey, my horse can do math. Come over here and you can point to this board, give me $1, you can point to the board, ask the horse a math question. If you do $5, you can ask the horse your own math question, like getting money for the horse doing math. So, spoilers there. So a person from the audience would say, Clever Hans, what is 2 plus 2? And the horse would clomp its hoof. It would go 1, 2, 3, 4. And it would stop clomping. And people would be like, wow, this horse can do math. Someone else said, no, that's too easy. It must have been trained on that question by the owner or something like that. I'm going to do a really tough question. Whatever the tougher question is. But the horse would clomp out the correct answer. So it appeared that this horse could do math. Good job, horse. But horses can't do math. So how was this horse getting the questions correct? Because it was. Most of the time, it was getting the questions correct. One of the biggest things was the body language of the people around them. So the horse is here around a whole group of people. When you ask it a question, what's 6 plus 2? The horse clomps. 1, 2, 3, 4, 5, 6, 7, 8. And then it stops. As the horse gets closer to the answer, the body language of the people around, the experimenter, the body language of these other people, who you could also say might be considered experimenters in this example, changes. They start to get quieter as they're waiting and watching for the horse to stop clomping. And then as soon as it gets to the right thing, their demeanor changes. They get excited if it pauses a minute. So the horse has learned to respond to body language. What the horse does know, it's been trained to watch human body language, clomp, and then stop clomping. And then it'll get a carrot or whatever treat it was that it was getting. So it learned body language, which is very impressive. Very good job, horse, but it's not doing math. This is a really good example of what we'll call experimenter bias or expectancy effects. So the experimenters are expecting the horse to get it right or wrong, and they're changing their behavior as the horse is getting close to the answer. They're holding their breath, they're staring more intently, they're getting excited, and the horse picks up on that behavior and changes its behavior. So we'll come back to this example. So unfortunately, the horse could not do math. But how could we prove causation? Well, we can't use correlations. We talked about that already. Correlations give us relationships between variables, but it tells us A and B are related, not if A causes B or B causes A. So we must use experiments. You can also use longitudinal studies to get at cause, but we're going to focus on experiments today. So So yeah, quasi-experiments. We will talk a little bit about quasi-experiments, but we're going to focus most of our time on experiments. So what is an experiment? An experiment is a type of study where you're examining two or more variables. A lot of our examples will just use two variables, and you have to manipulate at least one variable and determine if the change that you made, the manipulation you did, if that causes a change in your second variable. So you must have control over at least one variable. You must manipulate one variable, have control over one variable, and measure the changes with these. So this is a pretty simple example. Let's say we wondered if test scores will be different in a loud room versus a quiet room. So our variables here, we have loudness as one variable and test score is another variable. So we're examining two variables, loudness and test score. So our control group or comparison group is here in the room with no noise, no sound. They're doing their math test or whatever test it is. They do their test and they get a score. So maybe their average score is 10 of 10. They did really great. Then our experimental group, they have a manipulation to the quietness, right? They have a loud room. So we have manipulated the loudness variable. We're manipulating loudness. They have a loud room. They get a score of 7 on average. So this group got 10. This group got 7. So does that show a causal effect? Well, yeah. I mean, 4 people in each sample is really small, but it's just an example. So maybe you take 400 people in the quiet room, 400 people in the loud room. And if you see a difference in those, you can be pretty sure that as long as you have control over your variables and there's not something else happening, this room isn't also hotter or also colder or also more stinky or something like that, that you're only looking at the test score and the loudness. You've manipulated loudness and you look at that test score, say, is that test score different between these groups? If so, you could say, well, it was probably caused by the loud room. The loud room led to or caused the lower score. So this brings up a couple points about causation. What are some of the basic logic points in causation? One is time precedence. If A happens and is consistently followed by B, and the opposite is not true, so A happens, then B happens, but never B and then A, we generally conclude that A causes B. So with that, there's a couple different kinds of causation. One is unidirectional causation. So this would be that you have heat maybe causing aggressive behavior. Another would be bidirectional causation. They can both cause one another. So one thing humans can experience is guilt can lead to anxiety, but also anxiety can lead to guilt. So really unfortunate bidirectional causation there, that they can both cause one another. And then non-causal covariation. So this is another way to say correlation. These are related variables, but one is not causing the other is not causing the other. They're non-causally covariating, they're correlating. All right, so with this, experimentation allows for us to manipulate variables that we're interested in, like the loudness variable just now. We're interested in, does the loudness affect test taking scores? It could be something like, hey, maybe one room we could play classical music, and another room we could play rock music, and we could see maybe maybe one works better than the other. Right? So you can use multiple kinds of manipulations. You can manipulate more than one variable, but the experiments just get more complicated. So right now we're going to stay with really simple examples. You can hold constant other factors. So what I mean by holding constant is the other variables in these rooms should be identical. The heat should be identical, so that's held constant. That other factor, that other variable of the heat, the temperature of the room is held constant. The time of day should be the same, held constant. Smell of the room should be held constant. So then you can know it wasn't because that room was stinky or that room was not stinky. You can say it was because of the loudness. So you hold constant the other variables. It allows you to see the effect of that one variable you're interested in, or the multiple variables if you have a more complicated experiment. But here we see if the loudness did make a difference in the test scores. With this, only in experimental methods is there a really clear specification for independent and dependent variables. So, and only experiments give you plausible causal relationships. So it's only in experiments that you can plausibly specify causal relationships. So because I held all the other factors constant, because the only variable different between these two rooms was because it was randomly assigned, there was a random assortment of 100 people in one room, 100 people in the other room. They all went to the same courses, or they all learned the same material. The rooms were exactly the same. The only thing different was that one room was quiet, one room was loud. My results, I can plausibly specify that the loud room caused poorer test scores. So that's what experiments are really useful for. And experiments are used in all sorts of sciences. Psychology is one of them, but many sciences use experiments. So let's define a few of these things. Independent variable. The independent variable is the one the experimenter manipulates. So in your notes really quickly, what was our independent variable in this example? So this variable was the one manipulated independently of its natural sources of temporal covariation. So you intentionally changed it. You intentionally changed this variable. You might also call this the treatment or the manipulation. So what one was this? The independent variable in this example is the loudness of the room. So one room was quiet, one room was loud. This is our independent variable. We changed or manipulated that variable. So what is our dependent variable? Dependent variable, you could think of this as kind of the final measured variable. Again, you can also have multiple dependent variables. Maybe they do a science test and a math test, both of those. Oh, well, I just gave the answer. It's the test. The test score is the dependent variable. But in this example, we have just one final measured variable. The dependent variable is the test score. So we want to see if that test score has changed based on manipulating the independent variable. So IV is independent variable, DV is dependent variable. So is the dependent variable, is it affected by or is it dependent on the independent variable changing? So quiet versus loud, did that change the score on the exam? So again, independent variable, the experimenter changes or manipulates that one. That is our loud room versus quiet room, our loudness variable. Our dependent variable is a test score, and so that's the final measured variable. We want to see if it changes based on whatever we did to the independent variable. So we could switch this around slightly. We could, rather than loudness, we could have one room with classical music, one room with no music, one room with rock music. And we could see, based on that independent variable of type of music, is one better than another? Maybe classical actually is better. Oftentimes when I study, I listen to music with no lyrics. So I think I would probably do a little better in a room with music with no lyrics versus a room with music with lyrics, as an example. So how do we measure independent variables or dependent variables? Well, some of the same ways we've been talking about all the way through the class. Self-report measures, behavioral measures, physiological measures. There's lots of ways to measure independent variables and dependent variables. So self-report measures are things like surveys. You measure thoughts, attitudes, behaviors. Did you do pro-social behavior yesterday? Yes or no? How likely are you to do pro-social behavior? Very likely, not very likely. How likely are you to vote for this candidate? Do you have positive or negative attitudes towards this candidate? These kinds of things are self-report. You're reporting about yourself. That can be one measure of either an independent variable or a dependent variable. Behavioral measures are direct observations of behavior. So I saw 10 people raise their hand, or I saw a score of 80 on the exam. So direct observations of behavior. I saw people sneezing. I saw people falling asleep. Whatever it is, it's a direct observation of behavior. So how many times did students raise their hand? How many people did a pro-social behavior? These are things that would be behavioral measures. And so that could be either your IV or DVs or both. You're measuring either through the self-report measures or behavioral measures. Physiological measures are responses, recording responses of your own body. So how much you're sweating, what is your heart rate, what are your hormone levels. Even brain scans are examples of physiological measures. So an example of using a physiological measure, we could take our simple experiment. We have people in an MRI. One group, well, an MRI is really loud by itself, but they're wearing earplug earphones. So they're wearing earplug earphones. One group has just kind of a silent white noise. It's very quiet. And as they're in the MRI, they are also doing a math test, right? The other group, they're in an MRI. They have the earplug earphones, but they are listening to loud music while doing a math test. So now we have two DVs. We have the test as a DV, and we have the brain scan as a DV. We can look at maybe what parts of the brain are active. Is it different between the group that had just the silent white noise or the loud music? We can look at that. So versus behavioral measures, how many times did someone raise their hand, or what is their actual test score? Self-report measures, maybe we could give them an assessment of how comfortable do you feel taking this test. That would be an example of a self-report measure. So with this, with all of our measures, we need to be concerned with some qualities of the measure. One of these things that can affect a measure is called a ceiling effect. A ceiling effect is when you get everybody or most people having high scores on the measure. So here is actually a measure of prosocial behavior. This was from one of my recent studies. Almost everybody said that they would do prosocial behavior. So the max score was 7. You can see most of the people, this is what, like a little under 70%, said on all of the things, yes, I would definitely do these things. I would definitely act prosocially. So you can see there's a skew here. It's not a normal distribution. It's very skewed this way. When you have a ceiling effect, it's hard to say anything about these low scores because there's very little data there. So that's important for experiments. That's also important for correlations. But when you have all high scores, when you have a ceiling effect, that can make it hard to determine things. So let's say you did an experiment and the one class was in the quiet room, the other class was in the loud room, and everybody scored 10. Everybody got 10 out of 10 on the math test. Maybe the measure was too easy, right? Maybe your math test was just really, really easy, and so what you did, your treatment, your loud room versus soft room, didn't matter at all. It can really, really impact your score. You could say, well, it doesn't make any difference. There's no difference between loud or soft room, but if that was all due to the fact that you had a ceiling effect, you can't say that you have a valid experiment there. Your data is not good, it's not valid, it's not getting at your true answer that you're wanting to get at. You want to know about the loudness of the room, and all you know now is, well, you might not know, but what you actually have is a ceiling effect. So the original measures of purpose had some of these problems. Most people scored really high. The newer measures of purpose we've created has a much more normal distribution. So this is the measure of prosocial behavior that I created. Still is not perfectly normal. There's definitely a higher average people responding here, but we have high scores, we have low scores. It's a lot more normally distributed than some other measures that might be of similar kinds of constructs. So with this, it might appear that your independent variable, loudness, didn't have any effect on test score, your dependent variable, because of the lack of that normal distribution, because you had that ceiling effect. Similarly, a floor effect is the opposite. So in a floor effect, you're getting all low scores. So maybe your test is too hard and nobody can get a good grade. Maybe your measure is getting just low scores for everybody and it's not a valid measure that way. So for example, if you take a survey that is made for a middle schooler, or even let's say a math test that's made for a middle schooler, and you give it to a fourth grader, how well do you think that fourth grader is going to do? Maybe the middle school written survey has words they don't understand, right? Or maybe if it's a test, a math test, there's concepts there that they have not heard of yet, right? So it's going to be too hard. So it's not going to be a good measure. You're going to have really low scores. And if that is the case, again, you have the same kind of problem as a ceiling effect. You can't say it was your manipulation. Now you have a bad result. There's no difference. Everybody scored really low, and you can't tell if your manipulation, your IV, your loud room, had any change on test score. So here we've got a couple other examples of types of manipulation. So a straightforward manipulation is kind of like a simple manipulation. So something like you watch a video and that should manipulate you in some way. You read a written prompt and that should manipulate you in some way. You listen to a recorded sound. It's really straightforward. Generally these are a little bit easy. So here's an example. Here's one that we actually used in one of the purpose activities. We told people, hey, read the following quote. Think about its meaning. After that, write about that quote and what it means to you and what are the things that matter most to you. So they read this quote, they thought about it for a minute, and they wrote a response. Pretty straightforward. You can put that in a workbook, you can put that online in instruction, you can give that instruction in a class. Pretty easy to use in a lot of different contexts. But that was our manipulation. It was intended to help them think about what is most important, and as thinking about that, hopefully that increases their purpose in life. It ended up working in combination with other things, so the effect of this was little, but adding on other activities made the effect bigger. So another good example of a straightforward manipulation, I think I've mentioned this in the class before, is this guided mindfulness meditation that a team and I created. So we'll just watch a minute of this.
So find a relaxed, comfortable position, seated on a chair or on the floor, on a cushion. Keep your back upright, but not too tight. Hands resting wherever they're comfortable. Tongue on the roof of your mouth or wherever it's comfortable. And you can notice your body from the inside, noticing the shape of your body, the weight, touch. And let yourself relax.
All right, so feel free to go to this link later on and use it. We did see that for people who used this example of a straightforward manipulation, that their stress decreased, they felt more mindful for a few minutes. So the effect didn't last very long. It was about a 7-minute video, but this is an example of a straightforward manipulation. So something people could watch. You could watch it on your phone. You could watch it in a classroom. It's really straightforward though. You take in the content and that should manipulate you in some way. So it was intentionally designed to decrease stress, increase mindfulness, and it does. It was also a test, like proof of concept. Hey, can we actually, with these little lessons of guided meditation, can you make someone more mindful? Yes, you can. The effect doesn't last a long time. To get the big positive effects from long-term mindfulness, you need to have regular mindfulness practice, but this was kind of like, this would be a first taste of mindfulness, a guided meditation. After a while, you probably get to a point where you do the meditation on your own. But what we were testing is just that first initial bit. So that is a straightforward manipulation. So I'm trying to manipulate your purpose in life. I'm trying to manipulate your stress levels. And then I use a dependent variable measure. In these cases, I used surveys. But for stress, you could also use like hormone levels, sweat, things like that. So a physiological measure. So another example is a staged manipulation, and these are often a lot more complicated. You're trying to simulate some kind of real world event. You're trying to create some state. You're manipulating someone's maybe anger or happiness. You're intentionally trying to do that. So with this, generally these take more money, time, effort to do, and they can be hard to do consistently. So here's kind of an example of a staged manipulation.
Place like this street in New York City. If you were unfortunate enough to be the victim of a crime or taken ill unexpectedly, you might think that surrounded by all these people, someone would intervene. After all, isn't there safety in numbers? Psychologists say no. Research suggests that often a victim is less likely to receive assistance when surrounded by a group rather than a single bystander. When people are in a crowd, it's easier to pass the buck. It's what psychologists call the diffusion of responsibility. Liverpool Street Station in London, a busy thoroughfare for commuters. Unknown to these passers-by, Peter is an actor. As part of an experiment on bystander apathy, he's pretending to be ill.
Help! Help!
How long before he gets help?
Please, somebody. Help! Help me, sir. Please help me.
Helping would be inconvenient or even risky. He lies there for more than 20 minutes and no one raises an eyebrow.
Please, somebody help me.
It's always very distressing to watch situations like this where people are obviously suffering and no one's actually helping them. But what we have here is two conflicting rules. One is the rule that we ought to help, and the other is the rule that we ought to do what everybody else is doing. And here you have effectively a group of strangers who are exerting the pressure not to intervene, not to help.
So I'm not going to watch the whole video. I think you get the idea of that stage manipulation there. Feel free to watch the rest of it. They switch up the apparent gender of the person. So are people more or less likely to help depending on the gender? They also change the manipulation on having each of the actors wear nicer clothes, like something that a business person would wear. And so to see if they'll help quicker with wearing street clothes or business person clothes, they were a little more likely to help someone who was wearing business person attire than someone who was not in this specific case. But that's an example of a staged manipulation. You're creating some sort of event around things, some manipulation of the real world. They can get very, very complicated. But the main idea around these is you want to control all other variables. You want to manipulate just the variables you're interested in. And to do that, sometimes you need to make a really, really specific situation happen. So stage manipulations can be essential depending on what you are looking at. In some cases, you might be able to do something more like a straightforward manipulation. All right, so with this, another thing to think about with your manipulation is how strong it is. So for example, if you want to see how much people's muscle mass goes up, you can say, all right, everybody's going to exercise, all groups. Our manipulation will be with your exercising, level 1, use no weights. So no weights at all, just do these aerobic exercises. Level 2, so a little stronger manipulation, use 10-pound weights as you're doing these aerobic exercises. And then level 3, you're using 20-pound weights while you're doing the aerobic exercises. You would want all the exercises to be identical, things like that. Honestly, I should probably put less. I can imagine someone trying to do exercising for the first time and jumping jacks with 20-pound weights, probably going to lead to injury. So probably, but it's a good example, like no weights, 10 pounds, 20 pounds. This intervention level 3 is stronger. It's a stronger manipulation, but is this actually going to make the muscles grow more, or is it going to be too much? So that's one reason to have multiple strengths, is to see how much is needed. How much studying is needed to do well on an exam? Is it 1 hour? Is it 2 hours? Is it 3 hours? Is it 4 hours? Is it 17 hours? Right? At some point you probably get a drop off, like it kind of plateaus and you don't really do any better. So having different strengths lets you see about where the perfect amount of intervention is. So probably something closer to 10 in this example of doing aerobic exercises with weights would probably be more appropriate. And so that can help you see the patterns that let you know that yes, it is your manipulation. Your manipulation is best when it's at this strength. So we could have 3 levels of sound in a room. We could have very quiet, let's say 30 decibels and then 60 decibels. I think 60 decibels is actually like 10 times louder than 30 decibels, but just as an example of strength. So a simple experiment has 2 levels, on, off, no no manipulation or manipulation, right? So on, off, treatment, control, no manipulation, there is a manipulation. So our example originally, quiet room, loud room. So no sound, loud. That is the 2 levels of that manipulation. So the strength is 0 or the strength is 100, you could say. So usually this treatment, when you have only 2 levels, is as strong as possible. So highest weight, highest time, highest volume, just to make sure that you can see an effect. So you try to manipulate the situation in a way that you can see that your manipulation has some effect. So usually it's a very strong treatment. So if you were thinking like drug versus placebo, 100 milligrams of the drug versus 0 milligrams of the drug. So what pattern of results would we expect in a pre-post test design with 2 levels? Now keep that in mind, we'll talk about that. More complex experiments often have more than 2 levels. So you've got the quiet room, medium loud room, very loud room. You do studying for 30 minutes, 1 hour, 2 hours, 3 hours, so more than 1 levels. And that really helps you pinpoint. So high, medium, off, intense treatment, moderate treatment, control, a long treatment or a shorter treatment. All of these can help pinpoint exactly what kind of strength and give you evidence if you expect the most strong treatment to be the best treatment. Then having a very strong treatment, a medium strong treatment, and no treatment, you should see kind of a comparative increase, right? No treatment, there would be no increase. Medium treatment, kind of a medium increase, and big treatment, big increase, right? That gives you more validity to say, yes, our manipulation, our treatment made these changes. It caused these changes. Remember, that's what experiments are about, detecting cause. All right, so how do you choose your manipulation? Do you want to use a straightforward manipulation, just a video that people watch or a prompt they read? Or do you want to use a staged manipulation? And really for these, it really depends what would best answer your research question. What would best test your hypothesis? What is the best method? Can you do it well with a straightforward manipulation? Then go for it. Do you need a staged manipulation to really control all the other variables? Then you better do a staged manipulation, right? Even though it's probably going to be more expensive, be more time consuming, that's probably what you should be doing. So what does the theory say is going to be needed or would work better? You want to be able, with your experiments, show an effect, hopefully, if there is an effect. What do previous studies say? Are you using reliable measures? Right? So if our survey of stress was bad, right? If it was not a valid or reliable measure, our mindfulness study, even if it is actually making people more mindful, if our stress measure is giving floor effects, we're not going to know that our mindfulness study or our mindfulness intervention dropped stress, right? So you need good measures. And then also think about the practical cost. So straightforward manipulation is probably cheaper. If it's going to work and be able to test your theory or hypothesis well, use it. So staged manipulations tend to be pretty cost prohibitive. So that's why they're not done as often. And there's so many moving parts to control, even with, say, actors or something like that. It can be really difficult to get exactly the same kind of manipulation every time. If you're talking about a medicine or a drug, you might want to ask someone to say, hey, when you're using this drug, whether it's the placebo or the real drug, don't use any caffeine while you're on this. Because maybe caffeine can kind of muddy the results, make it work better or worse. And you want to get a really clear picture. So that's kind of the same thing. All right, so experiment requires at least 2 groups. You need your treatment group and your control group, 2 groups doing 2 different kinds of strengths of interventions. And with these 2 groups, they should be randomly selected or randomly assigned. So the difference between these we'll talk about in a second, but randomization, getting randomly into either group, reduces the likelihood that your results come from already present differences. So this picture kind of illustrates that. We have orange people and purple people. So purple people is kind of a hard thing to say quickly. But what we want, maybe the orange people are just better at math tests, right? The orange people are better at math tests. So if we have one group of all orange people, their score on math is going to be higher. So it doesn't matter what kind of intervention or manipulation we did. If all the orange people are over here and they're all good at math, well, then we're going to not be able to see an effect of our intervention. So maybe the purple people are the best ones at math. But either way, whichever ones are better at math or worse at math, we want them all randomly assigned to each group. So we want an equal number of purple people in this group as in this group. We want an equal number of orange people in this group and this group, right? So in real life, this orange and purple represents all kinds of individual differences. So you could think of it as there's all the different genders. You want a mix of all the different genders in the treatment group and control group. All different ages. You want a mix of ages in your treatment group and your control group. You want a mix of people with different GPAs in your treatment group, your control group. You want a mix of people who are in different majors in your treatment and control group, right? So someone who's in a math major because they like math, maybe they did well in math before, you don't want them all in one group, right? For your dependent measure being a math test. So we can't always know every single variable that might possibly affect the outcome. But if we randomize, then we do a better job. We're a lot more sure that it's not down to differences between the groups. So random selection is essentially like I have the ability to sample from every single person at Salt Lake Community College. I wouldn't take what's halfway through the alphabet? I wouldn't take the first half of the alphabet and put them in the treatment group, and the second half of the alphabet put them in the control group. So maybe there's some difference in their lives. That wouldn't be a good way to get a good mix of people. I would let a computer say, all right, give me a random selection of 40 people to my treatment group, 40 people to my control group. Right? I would randomly get them, and so hopefully I get a fair mix of genders, ethnicities, SESs, GPAs, all sorts of things. It's all randomly mixed between them. So hopefully the treatment group and the control group are pretty identical in what they are like on most variables. So that's why randomization is so important. So random selection, all participants have an equal chance to be selected. I have access to all Salt Lake Community College students, so I can select them for the study. So oftentimes in real life, we don't have the opportunity to randomly select from an entire population. If you want to study the US population, you probably don't have access to everyone, right? A big number maybe, but probably not everyone. Versus random assignment, it's what's most often done. Basically, whoever volunteers, you randomly assign. So all the MTurk workers who come to my study, one of the first things I do after they do the consent form, the computer randomly puts them in control or treatment group, or the high strength, mid strength, low strength treatment. So that is what I usually do, is random assignment. That's what a lot of studies do, because oftentimes you don't actually have access to the entire population. So assignment is taking your volunteers and then randomly assigning them. Random selection is you have access to the whole population and everybody has a chance to possibly be assigned to a group. So your control group is the group that gets a placebo or no treatment. The treatment or manipulation group gets the treatment. So randomization reduces the likelihood that those effects came from everybody with higher GPA being in one group than the other. So any other potential difference that could change the results is randomly split up between the two groups. All right, so with this being said, the larger and more representative the group that you are originally studying and then assigning, the better the randomization will work. So in this example, the little diagram here, we have only 6 people, right? So that's 3 orange people, 3 purple people. We cannot get a perfect mix, right? Because there's just not enough people. But if instead of 6 people, this was 60 people, we could probably get a much more even mix of orange and purple people, right? If this was 6 million people, we could definitely get a good mix. Probably all sorts of variables would be equally randomly into both those groups. Like, yes, it would still be possible with even, say, 600 orange and purple people. It would be possible for a computer just to as chance, put all the orange people into this group and all the purple people into this group, right? That is possible. So random assignment isn't perfect, but it's pretty much the best thing we've got. You can also test. You can test afterwards and say, hey, so I have these groups. Did all the orange people, did all the people with the high GPA versus the low GPA, did they all get in one group versus the other? So you can test that statistically too, just to make sure that randomization worked. So it's a good thing to do. All right, so with this, a lot of what we're doing is trying to get out confounding variables. A confounding variable is one that varies along with the independent variable. So with our math test or the room loudness, something confounding this would be probably GPA or maybe your math ability. So this occurs when the effect of the independent variable and that uncontrolled variable are intertwined. So you can't, when that happens, you can't determine which variable is responsible for the effect. So oftentimes these are called third variables, and we talked about them with correlation as well. And they exist in experiments as well. That's one reason randomization is important. That's one reason control is very important, and measuring these relationships with a lot of other variables to just make sure that there's not any other confounding variables. All right, so participant expectations. Participant expectations are things like their demand characteristics. So this is anything that informs the participant about the purpose of the study. And so yes, you do need to give informed consent or at least consent for studies, but based on what you tell or do not tell participants, it might let them know, hey, you are in the treatment group or you are in the participant or the control group, and you don't really want to do that. One interesting thing is that participants will also often try to either confirm a researcher's hypotheses or disconfirm what they think the hypotheses are. I've seen this with high school students. I've seen this with experts in the field that they think they know what you're wanting to look at. And so like looking at their open-ended comments has helped me to realize, oh, this person was answering in a specific way. Maybe we should remove their data. But oftentimes people will want to confirm or disconfirm your results. I remember one comment from someone, a high schooler, who said, this researcher was really cool because they arrived here on a motorcycle. So I put this response for every question. I'm like, thanks, I get you're trying to help, but actually if you had just responded honestly, that would have been the most helpful thing. So that was funny. Because we want natural behavior. We want the behavior to be as natural as humanly possible for people to interact with the world and our manipulations and our tests as they just would. So, placebo groups are the group that can help control for some demand characteristics. If everybody is told the exact same thing, everybody's like, here, you're getting this pill, take it once a day, measure your temperature every day, and then in a week, come back, we'll do a blood test. That should get rid of some of those demand characteristics, right? Everybody's getting kind of the same spiel, the same communication about something. This increases external validity because this is also probably what someone who gets the real medicine will probably get too, right? So that can really help with participant expectations and get rid of those concerns. We already talked about the example of Clever Hans the horse. The experimenters, the people around Clever Hans, are expecting the horse to get it right or wrong, and so their behavior is changing as the horse gets closer. So let's say I did an experiment in a high school classroom. In the classroom I do the real treatment in, maybe I'm more careful, maybe I'm more nice, maybe I am more attentive than in the room where it's the kind of comparison group, like we're doing an activity that doesn't really matter, I don't really care about it as the experimenter. My expectations could change the way I behave and change the way they behave. If that happens, you cannot say it was the independent variable that you manipulated changing the dependent variable. And that's the problem with these participant expectations and the experiment expectations. So experimenter bias, experimenter expectation, we might intentionally or unwillingly change the outcome of the study. So usually this is unintentional. It might be intentional as well. Hopefully not. Hopefully I've taught you enough about research methods. You're not intentionally trying to bias your studies. So one way to get around this, though, is single blind experiments, where the participant doesn't know what group they're in. Single blind, participant does not know if they're in the treatment group or the control group. They just know they're in a group, they know they're doing a study, they get their activities, and then they do their surveys, right? So single blind experiment. Double blind experiment is me as the researcher also doesn't know if they are in the control group or treatment group. So when I have the medicine bottle, the computer already put in and recorded on the barcode, and the computer knows if this is a placebo or if this is the real medicine. So I'm hopefully acting the same way with everybody I give this bottle of medicine to. So that's double blind. I don't know if it's the true drug. The participant doesn't know if it's the true drug or placebo. They might know it's possible, like with informed consent, they probably know it's possible that they might be in a placebo group. But when I give them the medicine, I don't know, and they don't know. This is what I've done with most of my studies online. So because it's a computer and I don't see the data till after people finish the study, basically someone volunteers to do the study, I have them read the consent form, and as soon as they sign that consent form and click next, the computer automatically puts them in either group. So then they start having a manipulation, then they get measured. Or sometimes I'll do like a pre-test, and then a few days later, or maybe a little later, then we do a manipulation. But basically the computer puts them in the two groups. So really the studies that I've done with experiments are generally double blind. The first experiment I ever did was actually like in person with people, the dart throwing example. And that one I was actually interacting with them, and it was single blind. They didn't know which group they were in. They didn't even know there were two groups, but I knew which group they were in, and so did the actors in the room. So definitely a validity problem for that first study, but I learned better methods. So double blind experiment, the participant and the researcher does not know which group they're in. All right, so some types of experiments. This is how I draw, and a lot of people draw, a post-test only control group experiment. So you can imagine time is going this way from left to right on the screen. The X is a treatment, so your loud room. So this is the loud room group. This is the quiet room group. They get no intervention. It's a quiet room. And then the O is a measurement, so the math test. So one group gets the loud room and then a math test. The other group gets a quiet room, then a math test. That is a post-test only control group experiment. This is the control group. This is the treatment group. This is the dependent measure that we're doing. So this is a post-test only. This one is a little different. You see there's a pre-test and a post-test. So again, these O's are a measurement. So maybe we give them a math test, then we give everybody this math test, then one group goes in a loud room, and then we give another math test, and this group does not go in a loud room. So that specific example of a study doesn't make quite as much sense. You wouldn't want to do the exact same math test the two times because they would remember it. But if it's a survey of like how comfortable they feel, and then they get a mindfulness exercise, and then they get a survey again of how comfortable do you feel, you can look at the change from this point to this point. Did their comfort level go up, or did their comfort level go down? Did their comfort level stay the same? What about stress? Something like that. You could do a stress assessment here and a stress assessment here. Hopefully you'd see maybe this group is a 5 and a 5 out of 10. And this group, maybe they went from 5, so they were the same as this group. So the groups were randomly assigned so that they had kind of equal stress. So 5 here, a 5 here, but then this 5 group that went through the mindfulness exercise got a 10 on stress. Or no, you'd be wanting stress to be lower, so got a 0 on stress. So that's a pre-test, post-test control group experiment. So what's so good about a pretest? Well, a pretest makes it possible to check group equivalence. So even though you're randomly assigning, there might still be differences. Maybe everyone who's way more stressed is in one group than the other group. Maybe everyone who's really good or really bad at math is in one group versus the other group. So if you have a pretest, you can say, hey, what's the stress level? Oh, both groups have a stress level of 5. We're good. They are equal. They are equivalent groups before the treatment. And then you can be more sure that any difference here was caused by your treatment. Everybody started with stress level of 5. After our intervention, the people who had stress level of 5 and did the treatment had stress level of 0. So that is a really strong evidence. That's stronger evidence than this example, where you would say, we did a treatment and then we measured their stress. This group had a stress level of 0. This group had a stress level of 5. That might suggest that the group are different, but you might say, well, maybe just all of these people were just more stressed. Maybe all the less stressed people were already here. There are some cases where you may not be able to use a pretest, but there's other cases where you may absolutely have to use a pretest. So with random assignment, it's less necessary. The better you randomly assign, the more basically you can say, hey, I did a post-test only experiment, and if you randomly assigned well with a big enough group, a good enough sample to begin with, that you're pulling from a population, then you could probably do a post-test only. But if not, pretest post-test is a really good idea. And even if you can, doing a pretest post-test is a really good plan. So for that, for example, we did that for our purpose tests. So we did tests of purpose, did an intervention, tests of purpose. So we saw people increase on that purpose. Then we did longitudinal follow-ups. We actually checked a few months later, like I think it was 2 weeks later, then a month after the intervention ended, and then another 2 weeks. So it was like a couple 2-week spans. And we saw that it went up the first 2 times and then kind of leveled off. So even a couple weeks after the intervention, they were still thinking about it. They were still searching for their purpose. And then after having not been doing the intervention for about a month, they stayed at the point that they were at. So large groups, more representative groups are better. So let's look at a couple types of experiments. Let's say you want to test a new drug to reduce anxiety. So you take 60 people, put them into 2 groups. One randomly assigned group of average volunteers has a sugar pill, and the other has your medicine that's supposed to reduce anxiety. After taking the pills for 1 month, you give each person a clinical interview to determine how anxious they are. So what type is this? So this was a post-test only. You didn't do an interview beforehand, you just did it at the end. So you've randomly assigned, but you're only doing the post-test only. So example 2, you want to test a new drug to reduce anxiety. You take 60 people with anxiety and put them into 2 groups. One randomly assigned group of volunteers has a sugar pill, and the other group has your medicine. When you bring them in to describe the study and give them the pills, you give them each a clinical interview to determine how anxious they are. Participants are sent home to take the pills. After 1 month, they come back, and you give them another clinical interview to determine how anxious they were. This is an example of the pretest post-test. Probably pretty clear because this is a lot longer description. I'm describing a pretest and a post-test. All right, so which of these studies is better and why? Put in your own notes, which study would you rely on the results for? The one where they get the pretest about anxiety before doing the treatment, or the one where they don't get the pretest before the treatment? So put that in your notes. So what types of problems could a pretest create? This is not something we've talked about yet, but could there be problems with a pretest? Might the pretest cause some change? So pretests can possibly cause problems. One problem is they can take more time, they tend to be more expensive. I have to go to the high school classroom this Monday and then also next Monday before doing the intervention, right? So that's a problem. You can cause changes in participants. You basically sensitize them. If you have the pretest, maybe pretest plus intervention makes a change. But maybe the intervention by itself doesn't make the change. Maybe it's only pretest and intervention, right? So you can sensitize participants. So the purpose activities, maybe they would have had no effect if we didn't do a pretest about purpose first, right? So another problem is attrition. You might have started with groups of 100 people in each group, but after they did the pretest, only 80 people come back in each group. That's a problem because then you have less people to get your stats from. So a solution to this is the Solomon 4-group design. So it basically takes the post-test only and the pre-test post-test design and lumps them together. So now we have 4 groups. 2 groups get a pre-test, 2 groups get a no pre-test. So these 2 groups, you can see this one is like this post-test only, and this one is like the pre-test post-test. So doing it all together, now you have 4 groups. This group gets no pre-test, but they get the treatment, then they get the post-test. This group gets no pre-test, no treatment, then a post-test. This group gets pre-test, treatment, post-test. This group gets pre-test, then post-test. So this allows you to see if there was any pre-test effects. You can compare these groups here to the scores here. So you can say, okay, this group, since they got no kind of treatment, they should be pretty equal to these groups on anxiety. Maybe all of these should be a level 5 on anxiety, right? Because none of them have had treatments yet. So you can compare that. You can compare and see if this group and this group are the same. And was there change from here to here as well? So it's a much stronger design. Again, this kind of complexity actually makes it better so that you can compare the groups in a lot of different ways. So there are additional type of experimental designs. You can add more groups, you can add more treatment levels, but for this class, that's all we're going to cover for experiments. Some examples of these types are independence group design or between subjects design. There's also repeated measures designs, counterbalancing designs, Latin square designs, matched pairs designs. And the key for all of them, to be a true experiment, you have to manipulate at least one variable and have at least 2 groups to compare, and you should have random assignment or random selection. Right? So each of these basically builds on the complexity, but you're still manipulating a variable, you still have at least 2 groups, and you still have some randomization. All right, so a quasi-experiment is a almost experiment. It's when you can't actually randomize to conditions. And this might happen in real life, right? So it would be really difficult for me to go into a high school classroom and teach a different lesson to half the students and the other half of the students, right? If they were actually watching it like on an iPad or something, you could definitely do that. You could have the neighbors getting a different intervention. But if I'm teaching an entire classroom, that's different, right? So a quasi-experiment's when you can't quite randomly assign 2 conditions. Or maybe you can't manipulate the IV. So maybe you can't actually make one room loud or one room quiet. Maybe the room is already loud or quiet. So you still may be able to do a quasi-experiment. You're still looking at the effects of the IV, the independent variable, on the DV, the dependent variable, and you can still make causal inferences. It's not quite as strong as a true experiment in most cases. Some are very strong though. So these inferences might not be as strong as a true experiment, but pretty good. So let's look at a single case experimental design. So this would be an example when you have an effect of a manipulation on one single participant. Basically, that person is their own control group. Now, let's say we had a time machine. We could say, hey, what's going to work best for my child? Is getting them tutoring going to work best, or is letting them play more going to be best for their math scores? I don't know what it is. So if we had a time machine, we create one universe where we give them tutoring and see what the outcomes are. We go back in time to the beginning, we give them more playtime, right? So then we would have them be their own control group. But I don't have a time machine. You probably don't have a time machine. So there's another way that we can actually do this. We look at a baseline as their level before any kind of treatment to see that is basically their own control. So the baseline is a measure of the behavior before the manipulation. So this is often used in like ABA, so applied behavioral analysis. It's also used in clinical and counseling settings or education interventions. So if you have one specific client and you're like, I'm wondering, will this treatment work to decrease their anxiety? You could obviously look at the research, say this will probably work based on their ethnicity, their age, the things they're going through, but you might not know, right? So start measuring their anxiety levels every time they come in. Then you start a new treatment and see, does their anxiety levels go up or down? So they become their own control group. Oftentimes IEPs, like an individualized education plan, will kind of build this in. They'll have some time of a baseline before the teachers implement a plan, and then you're monitoring the changes after that. So one example of this kind of quasi-experiment is a reversal design. So you get a baseline, you're looking for maybe the number of correct homework problems, or maybe turning in homework. Maybe a child is having problems actually turning in their work. So you get a baseline for 1 week, they turned in homework some of the time. They turned in some of their assignments. Then you start rewarding them. You start the treatment. You start giving them a sticker every time for every single homework assignment they turn in. So by the end of the week, you see they're turning in all their assignments. And then, beginning of next week, you stop giving them these stickers. Maybe the first day they're turning in their assignments again, but then they're like, nah, I'm not getting stickers anymore. I'm not turning things in. So that would give you good causal data to say, for this one individual, this sticker method is working. That's a reversal design. So you can use praise as a treatment. You could use stickers, some kind of things to improve performance in some way. Multiple baseline designs is kind of the same thing. Maybe you're trying stickers out with 3 kids in your class. So for Jim, you do 3 days of baseline measurement. At the same time, you're getting those 3 days of baseline measurement for Jen, and then for the third student, what's another J name? Let's just say J. J's a name, right? And a letter. So we've got Jim, Jen, and J. Maybe it was a bad idea to make 3 J names. Anyway, so for all these people, the first 3 days, you're just getting a baseline assessment. Maybe this is them yelling in class, so you want it to decrease. So after 3 days for Jim, you start praising when there's not yelling. You say, good job, Jim, you're not being loud, or something like that. You start reinforcing, you see and monitor and measure how much that treatment changes. Then about 3 days into doing that with Jim, you start doing that with Jen. And so you see what happens. Once you start the treatment, what are Jen's behaviors? And then after about 3 days of that, you do that with Jay as well. So when you do this, you've got 1 person, 2 person, 3 person, you've got good evidence that, hey, for these 3 people, giving them praise when they're being quieter in class helps. So that is a quasi-experiment. Again, this is just 3 people. You have 3 kind of control groups for themselves, but you're seeing, yeah, giving this praise is an effective treatment. So with this being said, you might do this if it's unethical to stop treatment for a reversal design. So let's say the treatment's something to save a person's life. You're not going to want to take that away, right? So if it's actually working, you don't want to remove it. So you can use multiple baseline, get a couple more people. And in some cases, you might have to do this when it's something like a really rare disease or something. You might have to do a quasi-experiment rather than a full placebo-type study. Also, if it would be unethical to not use the treatment, you can let people go a little longer without the treatment, but you're not going to keep it away from some people. That would be a good reason to use this kind of multiple baseline design. So with this, also, if you think the intervention's effect may continue after you withdraw the treatment, you might do a multiple baseline design. So if it's a cure for cancer, right, or something like that. So if you give the treatment and then you stop doing the treatment, the cancer's just gone forever. Well, reversing it, you're not going to see this kind of response, right? The cancer's not going to come back because it's just gone, right? So you can also do a multiple baseline design from across subjects, so with multiple people, or you can do it across behaviors. So let's say you have one kid with a bunch of problems. They're pulling hair of other kids, they're yelling in class, they're not turning in homework. You could do the same treatment for different behaviors. So you could start praising when they're not pulling hair, or start praising when they're not yelling in class a few days later, and then praising when they're turning in homework a few days later. So you can have multiple baseline design be across behaviors, be across participants or subjects, and you can also do it across situations. So maybe the place you're most concerned about the behavior is school. Maybe there's hitting behavior, a kid hitting another kid. So you start with reinforcing non-hitting behavior. So you get a baseline, then really quickly you start this intervention in the school. Then a few days later, you start that intervention at home. Then maybe a few days later, you start that intervention at grandma's house. So this is the same kind of thing across different situations, and it gives you good evidence, right? It's looking like it's really clear that this hitting behavior decreases when we start this intervention. So there's a lot of other types of quasi-experiments, but hopefully that gives you a really good idea. One group post-test only, so there's only a single group and they just get a post-test. That's a good example. One group pre-test, post-test, so there's one group, you don't have a control group. You compare their before score to their after score. You have a non-equivalent control group, so a group that's similar but not exactly equivalent. And then a control series design. The other one I want to actually share with you is the interrupted time series design. The interrupted time series design is a long series of observations. You could say like a really long baseline. And the reason this one's so useful is because it gives you fantastic causal data. So this is one thing that can be used in real life for, say, looking at policy changes or changes in lots of different things to make sure that they do or do not have an effect. So interrupted time series design, even though it's a quasi-experiment, it is still a fantastic design to get causal information. So with this, you need to have a lot of observations. The minimum researchers recommend is 50 before and after the intervention. So the interruption is really just the treatment. Whenever you do the treatment or start the intervention, in some cases it's one single event, right? Sometimes it's just a single event, one specific treatment, or in some cases it might be a policy change that at this date, now the law is different, right? So at this date, now federal law is different for how we think of marijuana offenses or something like that, right? So, or it could be an interruption like on this specific day, this specific dramatic thing happened. So you can look at it from that way too. So some kind of shocking revelation. Interestingly, when we look at overdoses over long periods of time, when a celebrity tends to overdose or even commit suicide, we often see behaviors of other people around them. So let's look at the overdosing example. When a popular celebrity ends up overdosing and it gets into the news, oftentimes for weeks and even months, we will see a decrease in overdoses. So like there's a general baseline rate of overdoses. But then after that interruption of learning that this specific celebrity died from overdose, people will drop their use, their overdosing of drugs, being more careful, not using as much, these kinds of things. It's a really interesting example of a natural kind of thing that happens with interrupted time series designs. So Australia fires and climate action might be a good example. So we saw like a specific amount of money being donated to climate funds, and then over recent fires in Australia a few years ago, we saw a big jump in climate action donations. So if there's a new law, you could measure that. So whenever the law changes, how prevalent was the offense before or after. A new form of surgery comes out. So a better way to do a hip replacement, for example. You can look at, hey, what was the level of infection before this started being implemented versus after it started being implemented. It's a really good example of a real life quasi-experiment. So before we had this method, now we have this method. Has it really helped and decreased infection? So with this, the interrupted time series design is the closest that comes to mimicking a randomized true experiment. It's probably the best quasi-experiment. So it's not perfect, but it's very good causal data for the real world. I want to show you this interrupted time series design. So in Taiwan, a few years ago, they had a lot of rapid development. But with this rapid development, additional products being purchased, a lot of consumerism, things like this, people were producing lots and lots of trash, much more than they had in the past, and the infrastructure was not there to take care of it. So this is literally an example from during that time, just garbage thrown out in the street, and it would be picked up. So it was creating a lot of environmental concerns. Things were trying to burn trash in the middle of a city, all sorts of things. But researchers were like, we need to solve this problem. So with this, it had the highest garbage rate for all countries at this time that this study was done. So with all these problems, the researchers and environmental people were like, we need to come up with a solution. So this was one proposed one. They decided, hey, we've got these two cities that are pretty near each other. They have pretty similar size populations. One was a little bigger than the other one, and they have about the same amount of this garbage problem. So why don't we try a new intervention? One of these cities, on 1 day a week, at this point, they were coming and picking up garbage every single day because there was just that much being produced. So rather than every single day, let's tell all the citizens that on Mondays we're not picking up garbage. We will not be picking up your garbage. So these people are going to have to sit in their homes with this garbage. Once they see that their homes are starting to pile up with garbage, just like our country is piling up with garbage, maybe they will decrease their garbage production. That was the hope, right? So they were thinking, we'll compare this one city where we'll do the intervention, and this other city, we'll use it as our comparison group. We're not going to do the intervention there. So they wanted to make the residents to store the garbage. Oh, also, these two cities were far enough apart that you wouldn't expect that they would just drive their garbage over to the other city. But really similar population size, city size, things like this. So they were hoping that the residents would reduce the garbage accumulation. So the intervention community was named this, the nearby comparison community was named this. So they got a baseline. They were measuring, I believe it was in tons. Was at the same time. Yes, they were measuring the garbage daily in tons. And so what patterns would they be looking for here? So think about it, draw it out on your own graph. If you want the garbage to decrease, you probably want the line to be up here and then go down, right? Maybe it even drops below this smaller city. It was a pretty similar size though. So that was what they were hoping. So they were hoping that the volume of garbage would drop and that overall garbage volume would drop. Or maybe it might have been Sunday that they were keeping the garbage and not picking it up. But the point is, 1 day a week, not picking up garbage. So they wanted to also see that there was no difference in comparison to no increase in the comparison community. So people weren't actually making the long, I think it was like a 45-minute drive or something, to the other community. But this is what they got. So they did this, they were measuring the garbage in tons for many months, so more than 50 points of data before they started the intervention. And you can see here, this is the treatment city, and this is the comparison city. So does it look like overall the garbage decreased for this group, for the treatment city? Unfortunately, this intervention didn't work. So what happened was people would still produce the same amount of garbage. With just storing it 1 day, it wasn't that much of a hassle. They stored it that 1 day, and then you can see these little spikes 1 day a week where there was just a ton more garbage produced. And then the day that they were only picking it up from like businesses rather than individual homes. So you can see a spike every week in garbage on the day that they're now picking up garbage. So this intervention didn't work, but it's a really good example of a really great interrupted time series design. You've got a long baseline for two similar places. You've got a long treatment for both places. So you could do this if you wanted to compare maybe two cities on their marijuana laws and how it leads to and is it causing increased or decreased use? You could look at medical things. So is creating a requirement to have masks in a building, does that decrease the prevalence of COVID? You can literally look up these studies right now for search specifically interrupted time series design studies. They're fantastic evidence of causal data here. So interrupted time series design, really great. Unfortunately, this specific manipulation didn't actually work. But luckily, later on, they found other interventions, and the garbage problem has gotten way, way better. So lots of improvements. So they did end up testing a bunch of different things. Some things worked really great. So they are doing a much better job now. But this is a really clear example of interrupted time series design. So with experiments, internal validity is about, can you attribute the results to your independent variable? Going back to our very first example, is our test score dependent on the loud room or the quiet room? Do we have the control over the variables enough to say that being in the loud room caused the lower scores? So we need to be able to draw that kind of valid causal relation from the data. True experiments require randomization. True experiments require at least 2 groups, and true experiments require at least control over one variable. So if you don't have randomization, you don't have 2 groups, or you don't have control over at least one variable, it is now a quasi-experiment, and it can still be good causal data like that interrupted time series design, because you can't, going back to the interrupted time series design, to randomize these, you would have to say, hey, half the people here, you just randomly say, move to the other city, and you're not going to do that, right? So for a true experiment, you need randomization, you need at least 2 groups, and you need control and manipulation of at least one variable. So without those, you do not have a true experiment. So why is randomization so important? It's because we need to be able to have our groups be pretty equivalent. We need our groups before the intervention to be pretty equivalent. All right, so that is all about experiments. Hopefully you have a lot better understanding. Hopefully all of the examples here were clear to you, and hopefully you can see and understand a lot more about experiments both in psychology as well as other fields.